In this lesson, we're going to look at how to use implicit differentiation to find the derivative of a function. So first I've got a quick do now question that's really already answered. It's just kind of to have a reference to come back to after we use our new technique. So we know that if we look at y equals 2x squared minus 3, that its derivative, which we can call y prime, is 4x. So we're using the power rule for the first part, and then the derivative of your constant is 0. All right, so we'll come back to that just to verify our answer when we use our new technique to do that. Okay, so our implicit differentiation technique is based on working with what we're calling the implicit form of the equation. Think of implicit as the word implied. So in the top row here, you've got y equals 2x squared minus 3. That's an explicit equation because it's already solved explicitly for y, right? Y equals a function of x. And the one underneath it, you want to think of that equation can be rearranged so that it could be written as y equals, but the form that it's in right now, it's not written that way. So this is implied to be a function of x in a sense, right? But it's not written strictly as y equals. And we want to be able to take the derivative in that implicit form rather than having it be y equals all the time because some functions are really difficult to write that way. So a few notational things here. We want to remember that capital D with the subscript x means just to find the derivative whose function's independent variable is x. And that dy dx is another way of basically saying the same thing, so that the function's name should be y equals, and the independent variable should be an x, all right, for that notation to make sense. All right, so at the bottom here, I'm going to kind of show you by almost breaking this up into two sides how the derivative would look like in our standard method versus how it would look for this new implicit method. So I'm going to take the derivative of both sides of my function or equation in this sense. So on the left, I would have just a derivative with respect to x of y. And on the right, we've got the derivative with respect to x of 2x squared plus 5. So again, the one on the right is the one that is familiar to us, right? It's derivative with respect to x of an expression that has x's in it. So those variables agreeing on the right side makes it your standard derivative. So if I just carry my equal sign here, I'm just going to write my usual 4x like we did on the do now question. Okay? But for the left side, what I want you to pretend is that you don't see all this stuff on the right side, including the function itself. So again, pretend I'm getting rid of all of this. And I just want another way to represent the derivative with respect to x of a function y, but pretending that we at least know that y is a function of x, but we don't get to see the actual expression. So using our symbols from above, we got this dy dx thing happening, right? So we can say that the derivative of a function y with respect to its variable x can be written as just dy dx. Okay, so that symbol dy dx is just a general way to represent the derivative of y with respect to x. And let me get rid of my cross out here so we can see. Basically, we've come up to the same conclusion that the derivative equals 4x. Okay, now more importantly, I want to do the same thing on the right side of the page. Right, and the key is that now I've got y cubed. Right, so on the left side, we have this term y that's assumed to be a function of x, and we're pretending we don't see it. On the right side of this, like in the right column, we actually do see the expression and can do a normal derivative rule. So on the left side, I'm going to think about taking the derivative of y cubed, pretending that there's x's in there that I don't get to see. On the right side, I'm going to do this in explicit form, where I can see the x's. So again, on the right side, that's an easy one, right? I'm sorry, this is cubed, right? On the right side, it's relatively straightforward. It's a chain rule question. So the derivative of the outside rule is that something is cubed, right? So we're going to multiply by 3, keep whatever's inside the parentheses the same, and reduce the power by 1. So make sure that you're not replacing this 2x squared plus 5, right? And at the end, it's times the derivative of what's inside, which in this case is our 4x. Right, so what I want you to see is if we pretend that we don't know that right side stuff, that we can still implicitly represent something with the same structure, the derivative that's going to have the same format. So what I'm looking at is now on the left side is a y term that's assumed to be some function of x's, and we're pretending that we're not seeing it. Its derivative from the chain rule would still be to start with the outside rule. If whatever y equals is being cubed, it would be 3 times whatever is in there and then squared, just like I did on the right side. The only thing is, since I don't know what y equals, I'm just going to call it y. And then what's representing the derivative of what's inside, like we did as 4x, is now just the derivative of whatever y equals. So I would, in symbols, just represent that as dy dx. Now, typically, I wouldn't write the parentheses around the y because you don't need them. But 3y squared dy dx and 3 times 2x plus 5 squared times 4x is exactly the same structure in the way I've written them. Okay, it's just that on the left side, I'm pretending I don't know what y really equals. So let's try to look at an actual example to make this more realistic. Okay, so here's the implicit form of the question from that main page of notes. Okay, so I've got this 4x squared minus 2y equals 6. And I want to find the derivative implicitly rather than rearrange it so that it's y equals. So my directions here say the first thing that we want to do is to take the derivative of both sides of my equation. So I'm going to take the derivative with respect to x of my 4x squared minus 2y, that's the left side, and then the derivative of my constant 6 on the right. Now, because we have rules that say I can split up the derivative on the left side because it's subtraction, I'm going to break this up into the derivative of 4x squared, and then minus the derivative with respect to x of 2y, and then that equals the derivative with respect to x is 6. In fact, you can go directly to that second step in the future if you like. So whenever it's a derivative of something that's in terms of x or a constant, it's a normal derivative. In other words, my first term, I'm just going to go straight across and evaluate my derivatives. So the derivative of 4x squared is just 8x. And then I've got minus. And now when I see that I've got mixed variables, that it's a derivative with respect to x of a y term, I know it has to be implicit. Okay? So this is the derivative of 2 times y, right? So this is sort of your constant multiple rule here, is that I'm allowed to just carry the constant through and then say now it's times the derivative of whatever y is. Now we don't know what y equals, so again, we're representing that as dy dx. And then on the right side, the derivative of my constant is 0. Okay, so there, that middle part was my implicit part of things, really, where I had to multiply times dy dx. Now all that's left is that since dy dx represents the derivative of whatever y is, if I get that alone, it's representing the derivative that I was after to begin with. So if I bring that term to the other side, I get 8x equals 2 times dy dx. Right, and then dividing by 2, my dy dx is 8x divided by 2, which we know is 4x. So that's why I had that do now question, is it checks out to be the same result. Now, I wouldn't suggest it for this given problem, but because it's easy to rearrange things, but there are others where you won't be able to, and this technique is going to be necessary. Okay, so I've got one more example for you guys to see if you can handle it on your own. So here's x squared plus y squared equals 9. Right? This is the equation of a circle. So it technically wouldn't be a function if we looked at the whole graph. So we'll have to discuss more of this in class together, but we're really only selecting a portion of this circle. It could be the top half or the bottom half, but we want to look at some portion of the circle so that the resulting graph still passes a vertical line test. So we're assuming in this case that if we arrange this to be y equals, that we can make y equals a function of x if we wanted to. So it's implied to be a function of x, but we still want to work with the form that it's in. All right, so go ahead and take your derivative, and you can check your result when you're finished. Okay, so first step is take the derivative all the way across, right? The derivative of each term. The derivative of your first term is your normal derivative 2x. The derivative of y squared is your power rule. So we multiply by 2, reduce the power by 1. But really, because y is an expression, this is the chain rule form, right? So the derivative of what's inside is your times dy dx, and then it equals your constant 0. Simplifying a little bit by dividing by 2, I get to here. And then finally trying to get my y term alone, I end up with dy dx equals negative x over y. Okay, now this is the first time you've seen a derivative that still has a y in it. Okay, but that really means that if we want to calculate the slope of the tangent, we would need both the x and the y coordinate of the point of tangency to do that. And in class, we'll look at some examples of how we would deal with that. Okay, so that's it for this lesson. Thanks very much for listening.